Okay, so if I want to take the 2 into the radical, if you, right, to take it out, you cube root it. To put it back in, you cube it. Okay, so that is an 8, which means inside we have 5 times 8, which is 40. Okay, the x's. Somebody else tell me how to do the x's. Yes, Josh?
Since it's a cube root, you would do, because if you took that x, it would have to have been x cubed on the inside. So you put in x cubed, basically, and then when you add x cubed to x, that equals x4.
Okay, so we have to put the x back inside, we have to do a cube, which means we end up with cubed times x, and then you add your exponents. Fantastic. Okay, y's? Yeah?
You cube your y to the third, which gives you y to the ninth, and then you add the other y to the y.
Yes, okay. So those are those exponent rules you're reviewing. So then you get y to the 10th. Now, you can always write it out over here. Right? This is what would be inside the radical. Notice if you were trying to go back to simplifying it, you can check. Those are all the perfect cubes. What stays in, what comes out. All right, nice work. Okay, is there another question I want to ask? Those giant numbers. Don't you multiply 54 and 16? Just maybe start that factor tree. No calculators. You are going to get better at your arithmetic. Or be more calculated. Okay, we'll leave the number alone and do the grade. Yes, I know. It's that 54 and 16. That's the most annoying part. And actually, not so bad. All right. Number 2. Here we go. Volunteer. What do I get? How about just the answer part? Chris, go for it.
6xy, 6x squared y cubed z cubed radical z.
Okay, rad z. Great. Okay, so because to start, all of those things are perfect squares, and then the z, you just split up into the perfect square. Okay, perfect. Okay, absolute value. Somebody else, where does the absolute value go? Yeah. Not quite. Tell me, okay, tell me why you want to put it there, because it's kind of like a maybe, so. Okay, so you're mixing up the pattern. Even root, even power, odd result. So where would it go? Yeah, there it is. Okay, on the y. Even, odd. That is the only pattern of roots and powers that gets the absolute value. All right, number 3 or 4. I'll let you pick either. Anyone want to give me a first step? All right, Josh, go for it.
So for number 3, I was doing, but when I had 54,
Mm-hmm.
I took out,
Yeah.
96, and then I got, wait, oh wait, no, I took out 27 and 2.
Okay, so 2 and 27. Fantastic.
Then you get, 3 cubed is 27.
Okay, so you're saying the 3 comes out.
And then you can put, 2 on the inside, yeah.
All right. It's a great start. Okay. Anyone want to tell me what you would do with the other one? The other radical? Sure, Lex.
Take 2 out of it.
Okay. So 8's the perfect cube, so the 2 comes out. And then the 2 stays. Sure. And then you can multiply these things together. Outside goes together. Inside goes together. Now, notice, when I am multiplying these two things together, I'm looking really closely at my numbers because you might have to simplify again. Like, before you box your answer, you better make sure there's no perfect cubes that are left, okay? So I'm looking at 2 times 2. Okay, that's a pair. There's no cubes in there, no perfect cubes. So I'm just going to say 4, x to the 9th, y to the 8th. And then I'm going to simplify. Now I'm pretty confident about the 6 outside and the 4 inside. But I need to take care of the variables. So somebody else. I'm going to start popsicle sticking. How would, like, can you tell me why it's x cubed?
Because x cubed times x cubed.
One more time.
X to the 9.
Yes, x cubed times x cubed times x cubed. Those are the exponent rules. So look at this. If I take 9 divided by 3, it tells me how many groups of 3 I get, which is 3. Okay, so we get 6x cubed. Fantastic. Jonah, what do I do with the y's?
It would be y squared, and then you have 2 left numbers, so that's 2 times.
Perfect. Okay, because if I want a groups of 3, I'm going to put y6 together because that's 2 groups of 3, and I'll leave the y squared. And so then we get cube root. So be careful not to like lose anything. So I get a 4 and y squared. Fantastic. Okay, right? That's perfectly acceptable to simplify your radicals before you multiply them because then you're multiplying smaller numbers together. Great idea. Just make sure you check that final radical. Yep.
How'd you get the last part again? Like the 4, like radical 4.
Okay, so this part is a perfect cube, so there's no x's left inside. Okay? This part, y to the 6th, is the perfect cube. And see this? Y squared is left over, and 4 is left over.
Oh, I see.
Okay, good question. All right. Luis, what would you do first for number 4?
I have no idea.
Okay, so look to your right or your left. There's, like, tell me one thing you can do to simplify this. There's a couple different answers. So, all right, I will come back. I'm going to ask someone else to start the problem, then I'm going to ask you to answer it. Okay, Ariel.
I guess factor of the factor of 48.
Factor 48. Okay, so you want to look for a perfect 4 in 48. That's reasonable. I'm going to just do it over here. Okay, so 48 is 2 and 24, 2 and 12, 2 and 6, 2 and 3. So I do end up, there's the bottom of my factor tree. And so, sure, I do end up with something I can simplify here. Okay, that's one way to do it. Sure. So 4th root of 3x7y. Okay, and so, okay, where's my grouping? There's my 4 of a kind. Okay, there's my 4 of a kind. So the 2 comes out, and the 4th root stays, 3xy5. Yeah, I mean, that's a decent first step. Now, there might be a shorter way to do this problem, but I'm taking your input here. Okay, something else I can do. Take x out on the top. Sure, I could take an x out on the top. So x 4th root 3x cubed y over 2 4th root 3xy5. Okay, anything else I can do? Sure, back here. Why, yes. If the numbers are both inside the radical, you can simplify them. Yeah, those things are going to reduce to 1. Fantastic. Okay, so I got an x of 4th root, so we'll just go x cubed y, 2, 4th root, xy to the 5th. Okay, what else? Yeah. Hold that thought. That is true, but before I rationalize, I want to maybe finish simplifying what's in front of me, okay? Because rationalizing is what we're going to do today.
Take x out from the bottom, so then you have x squared on top.
Oh, so Maya says, why don't you just simplify those two things also? Just like we did the 3's, let's simplify the x's. I like that statement. Because I'm going to run out of room here. What if we do the same thing to my y's while we're at it? Right? Reduce and simplify both of those things. So we get x 4th root. So we're going to get the x squared on the top. And we're going to get the 2 4th root y 4th on the bottom. Okay, I'm not quite finished. What else? Ooh, Tessa. Take the y out of the bottom. Okay, so x 4th root x squared over 2y. Whew. Okay, so Davin, the reason I said hold off on rationalizing, you didn't actually need to because the whole denominator radical simplified without that step. Okay? Wow. It's a whole lot of steps, guys. Notice that no one mentioned to simplify this thing at the start. You all started by simplifying the radicals separately. But watch this. Okay? See all that space it took me? What if I just reduce my radical to start? 3 and 48 is 1 over 16. x7 and x is x to the 6th. Y and y5 is y to the 4th. Voila! 2 steps later and you're finished. Okay, so the top comes out as x 4th root x squared, and the bottom comes out as 2y. Why not divide first? When you divide numbers, they get smaller. Okay? That's why maybe you want to divide first so that you deal with smaller numbers until, right? Make the numbers smaller as soon as possible. Now over here, when you decided to simplify the radicals before multiplying, that did make the numbers smaller. That's why that was a good choice. But here, it just took you a really long time to get to the answer. Okay, so make sure, even though there's multiple paths to the answer, try to pick the easiest route. Okay, this is the part of this unit that I like. Okay, so rationalizing means the denominator becomes, it's like an action. Make the denominator a rational number. Let's try that. Let's say that. Make the denominator a rational number. Rational means no radical. There's that vocab word again from polynomials. Rational means no radical. So we are trying to make the denominator not have a radical. All right. So here we go. We're just going to do some examples here, and then I will sort of formalize it afterwards so that you can kind of see how it works before we put it in an abstract term. So if I have 2 over root 2x, now that is a square root. I need to multiply by something so that I can get this radical out of the denominator. Okay? Now, it's a square root. How do I complete this perfect square? I've got 1, 2, and 1x. Multiply it by root 2x. Yeah, I got you. Okay? On the top and the bottom. Oh, remember that fancy form of 1? Yeah, it's similar to when we use the conjugate with our eyes. Same thing. Fancy form of 1. Because whatever I'm doing, I'm only trying to like rewrite this or simplify it. I'm not trying to change it. Okay? So, look at that. Now you just multiply the top of the fraction and the bottom of the fraction together and then simplify it. So the top is 2 root 2x. The bottom is 4x squared, which is magically a perfect square because you chose it so. And simplify. Okay, so we still have 2 root 2x on the top and then 2x on the bottom. And reduce the 2's because, you know, right? If it's outside the radical, you can reduce it. If it's inside the radical together, you can reduce it. So my final answer is 2 root 2x over x. Okay. You know, 3 root x over square root of, I need something good here. Okay, 6 6 that's too easy. No, I'm going to keep the 6. I'm thinking of the variable. I don't know. Someone give me a variable with a power.
Next to the fifth.
Oh, I like 5th. That's actually a good choice. Okay, guys. What now? You want the fewest steps possible. What might you do? Rationalizing is not your first step. It's your last step.
Cancel out your x's.
These x's are both inside the radical. You should simplify to smaller numbers before you do the operation. Right? Just like in that warm-up where it took you guys like 7 steps and took me 2 because I simplified it first to smaller numbers. So let's simplify to smaller numbers. So we get 3 over. Oh, see any perfect squares? Mm-hmm.
You can pull out x to the fourth.
X to the 4th is a perfect square. There's no rationalizing needed for that. Okay. X squared root 6. Okay. Now that I think I've simplified, I'm going to rationalize. Right? You want to multiply by the smallest number possible. Not the biggest number, not just slap down a radical and like do all this giant multiplication. Smallest radical possible. So you've got to think ahead about what's gonna simplify. Okay, so the only radical I have is 6. And I look at this and 6 is 2 times 3. So there's definitely no perfect squares in there. So I'm going to multiply by root 6 over root 6. So we get 3 root 6 on the top. And I get x squared root 36 on the bottom. Oh, but root 36 actually simplifies because it's a perfect square because I made it so. Okay. Just because I'm running. I'm just going to bring this up here. So we get 3 root 6 over 6x squared. Reduce. You're like, gosh, Missy, this is a whole lot of steps. Kind of like that problem we did in the warm-up. Could this possibly be done shorter? Yes. Okay, so I'm getting there, but I want you to understand that we're just simplifying and then rationalizing. So here we get root 6. Because I know when you get into like a little quiz or a test, you're going to like take a step back and you're just going to start simplifying radicals. And then you're going to be like, oh, I'm supposed to rationalize. Okay. Here we go. We are developing our knowledge. Okay. 4 root x y over 54 x y squared. Okay. Wait. Simplify if possible. Now, that could mean a lot of different things. I see x's, I see y's, maybe I see a perfect square. Okay? Simplify what you've got in front of you. Then we will rationalize. There's 2 things you can simplify. You've got some dividing, and you possibly have a perfect square that can be dealt with. Oliver? Where are you, Oliver? Oliver, there you are. Give me one simplification step. What do you want to do? Fantastic. Okay, great. The x's reduce. Love it. Luis, what else can I do to simplify this?
Or you can get rid of the y on the top. Like,
Yeah, okay. So the y's are going to reduce with and leave just one on the bottom. Okay, awesome. And okay, because this is kind of two steps. Just a 4 on the top. Okay, cool. Root 54y. Now, Leanna, what's one more thing I can do to simplify this radical before I try to rationalize? Yeah, so 54 is 9 and 6. 9 is the perfect square. Fantastic. So I'm going to take out the 3. Now I'm ready to rationalize. And it looks a whole of a lot nicer than the starting point, which would have me multiplying by 54xy squared. Okay? No. Smallest radical possible. Okay. Now that I know the radicals can't be simplified, now I have to rationalize. Okay, Lucas, what am I going to multiply by in order to get rid of this radical in the denominator?
Would you multiply 4?
Say it again.
4? No.
Not 4. So the radical is here. This is the thing that I'm looking to, we'll say, match up, right? Because I need to multiply by something so that root 6y will simplify completely. You got to turn it into a perfect square.
You got 6y on?
Yes, 6y. Because if you multiply by root 6y, this turns into 36y squared, perfect square. Okay, so whoop, here we go. So I get 4 root 6y, 3 root 36y squared. Okay, 4 root 6y over, okay, can we do this? 18y. Now, I've written one tedious step, one extra step I've written. Yeah?
Oh, wait, I'm not sure. I said you have to, I know you have to simplify it after.
Yeah, you do. Okay, so let's do that. 4 and 18, which are both outside the radical. So I'm going to reduce those two numbers. Okay. And as I'm boxing my number, I'm like, there's no perfect squares left in the radical. Okay. I wrote one step that doesn't need to be there. Yeah?
The 3 over 36y squared.
Yeah, guys. Do you really need to write that? No, because you're smart enough to know that this right here is just going to turn into, right? Because you know the 6y is coming out of the radical. You know that. You know it's coming out of the radical. You don't need to write that extra step in there. Okay. That was square roots, guys. Now we're doing cube roots. It doesn't get any harder. This is as hard as it gets. Okay? Number 4. Cube roots. Okay. I'll just start counting again. Okay. Cube root of 2 over, all right, 9x. Sure. All right. Do I have any perfect cubes? No. I got a perfect square, but not a perfect cube. Can 2 and 9 reduce? No. Okay, so there isn't anything to do here. So I need to multiply, right? There's no simplifying, there's no reducing. So the only thing left to do is to rationalize. All right, so this is going to get a little interesting. I'm going to write 9x over here because that's the denominator, right? I'm not looking at the numerator, I'm looking at the denominator. And I'm going to make a little factor tree. Because 9 is 2 3s. This is where the cube root gets interesting. I'm not going to multiply by 81x squared. Why would I do that? That's a giant number. Okay, in red, I'm going to complete my groups of 3. You see that? I'm making perfect cubes, not perfect squares. Squares is just 2 of a kind, which looks like you just copy the denominator. Okay? But you're making a perfect square. Here, I need to make a perfect cube because that's what's going to simplify. So look at my factor tree and notice that in red, to make a perfect cube, I need 1 3 and 2 x's. So this is what I'm going to multiply by. 3x squared. 3x squared. And it's because of I'm completing the groups of 3. Because that's what's going to simplify. Yes?
So those numbers are like allowed to be used because they're technically factors of the other things that would like
Yes.
rationalize it?
Exactly. So I'm going to do the multiplication. So the top is going to be 6x squared. And the bottom is going to turn into 27x cubed. And you're like, oh, that's a perfect cube. 27 is 3 3 3. That's what simplifies. Okay, so cube root 3x. See that? Because I chose the 3x squared strategically to give me the smallest perfect cube. Because if you pick a big number, guys, it's going to take you a whole bunch of steps to get to the final answer. I'm trying to get you to the smallest choice first. Yes?
Couldn't you simplify it more if you like divided 6 by like you put 7 by 3? And like you simplify the x's?
No, okay, be careful. Okay? Because this is my perfect cube because what you just suggested would take you back to this. Okay, which, fine, but keep in mind the direction you're headed because that's the perfect cube. We're headed to no radicals in the denominator. All right. Another perfect cube. Here we go. All right. Cube root of 3y over cube root of 4x5y4. Okay. Ooh, I see lots of numbers. Maybe I should simplify first. Okay. Let's go with Sierra. Just one thing you can simplify up here. Anything you notice?
The x.
Okay, what do you notice about the x?
No,
I agree. The x can be simplified. How does it simplify?
the second you called on me every single time.
Okay, that's totally fine. We'll go with this. Davin, tell me one thing you can simplify.
That's weird.
Say it again.
Y on the top and
Okay, the y on the top and the bottom. Sure. Okay. Stevie, do you know how the x will simplify? Maya?
You can take it out of the radical.
Okay, so the part of this x to the fifth, x cubed, x squared, so there is a perfect cube here, right? You can do the root or you can divide if possible. Okay, so the numerator is going to have a 3. The denominator is going to have, the 4 is going to stay. The x is going to come out. The x squared stays, and I get y cubed. Okay, so that was my first round of simplification. Is there any other simplification? Yep. Fantastic. Yes, you can pull that y out as well. Okay, if you see this all in one step, go for it. If it takes you more than one, no problem. Okay, so we got a cube root, x, y, cube root, 4x squared. Okay. I've done my simplification, but I still have a radical left. So now I rationalize, right? First you simplify, then you rationalize. Okay, that's when I'm going to do my little factor tree to make sure I can find the perfect cubes. Yes?
Like the radicals, to make it 2x.
Ooh, yes, you would. Okay, so I'm just going to write my 4, and I know that's 2 times 2, and my x is x times x. Okay, I need to complete the cube. I need to complete the cube. So that means I need 1 more 2 and 1 more x to make my perfect cubes. So when I rationalize, I need 1, 2, and 1 x because that's what's going to make the perfect cube. And then I actually multiply straight across. So cube root 6x xy cube root 8x cubed. Yes, that is a step I don't necessarily need to write. Okay. I guess I'm going to have to go straight across. Okay, so cube root 6x xy, right? Because the 2x is what comes out of the radical. Whew. All right. You ready to try a cube root all on your own? Yes, you can do it. All right, you're getting there. I'm just going to squeeze it up there. Okay. Oh, that's a mean problem. Okay. Oh, perfect. Okay. Cube root of 2x squared y over 6xy cubed. All right. Go for it. Okay. First up, we're going to go Stella. Tell me one thing you can do to simplify this.
I subtracted the x and the y.
Okay, so here we go. So she said that she reduced the x's and the y's. Okay? Jack, what's one thing that you did to simplify? I'll sort of write down what we've got so far. So x and y squared. Okay, hold on. Shh. Whisper so I can hear. Okay, hold on. This is on the top. This is on the bottom. Can you simplify them? Yes. Okay. So then we do this. So in this particular case, there's like all these things that can simplify under the radical. I don't really need to write a 1, right? It's just a 3 in the denominator. Okay. Vince, is there any perfect cubes that could be simplified? No. Okay, so that means our final step is question or answer? Question.
Why wouldn't you just pull the x cubed out from the
There,
beginning?
the y cubed.
Do that, yeah.
You could pull it out. They just happen to choose reducing first.
Okay.
It's not wrong.
Okay.
Okay. So watch our final answer. We'll probably end up in the same place. All right, Vince. What am I going to multiply to rationalize, which means turn this into a perfect cube in the denominator?
9y.
9y. Fantastic. Okay. So 9y. Can you tell me why you chose 9?
Because you need a cube root, and 3 times 3 times 3.
Yeah. So you've got 1, 3. I've got 1, 3. I need 2 more, which is 3 times 3 is 9. All right. And then why did you choose y to the first power?
Because you need y to the third.
Yeah, I've got 2 y's, so I need 1 more, and that makes my perfect cubes. Fantastic. Okay, so let's multiply. Cube root 9xy on the top. Cube root of 27y cubed. Woohoo! Perfect cubes. Simplify them. Right? There's that step I maybe don't need to write because I kind of already know that's coming. All right, so my answer is cube root 9xy over 3y. So did you still get the same result? Yes, so that's why that simplify step, it's just what you see. All right, guys. Fantastic. There we go. I'm going to do one more problem. This is it. This is your last problem, though. Binomials. What? Rationalize. Right, we're still rationalizing here. Don't worry, I'll do a little, what is that called? I'll do a little review next class also, like a little warm up to recap. Okay. Okay. Okay, I lied. It's going to be 2 problems, but that one's really, really short. What am I going to multiply by to rationalize this? Because really an I is a radical. Rationalize means no radical in the denominator. The conjugate. Right? How do you rationalize? You multiply by the conjugate. Now, this has a specific name. When we had those plain radicals, it doesn't have a special name. It's just you have to make the perfect cube so that when you simplify the radical, it goes away. Here, I'm trying to multiply by this fancy form of 1 so that when I multiply, the I disappears from the denominator. And so this is that conjugate. Okay, it's where we change that sign. And now I'm just going to multiply straight across the top, straight across the bottom. 6 minus 2i. I guess I could FOIL here. First, outer, inner, a last. Zoom that in for you. Canceled out. Okay. 6 minus 2i. All right. That really turns into a plus 1. That's it. How do you rationalize with binomials? It's this conjugate idea. Because multiplying by the conjugate turns it into a rational number. That was, right, that was the review. Recall. Now I do notice that that all of these things divide by a 2. So I am going to do that division here. Okay. Whew. I guess. Well.